forward to talking to you guys about my PhD thesis on robust autonomous spacecraft navigation and environment characterization. I'll start by motivating and defining my research problem, which is to enable more autonomous operations in space through the development of improved algorithms for navigation and environment characterization. So I'll describe relevant state-of-the-art approaches and their limitations, and then I'll describe these 5 key contributions that I've made, and I'll finish with a summary and future work. So let's start by motivating and defining this research problem. Autonomy is becoming increasingly important in space. It's not feasible for humans to manually oversee all operations of the rapidly growing number of spacecraft, which is near 5,000. Autonomy also reduces mission costs and is often required when the spacecraft must react quickly to its environment, for example, when operating very close to another spacecraft or a small celestial body. For example, autonomy is typically required in debris removal missions like LCD, and also for orbit servicing missions to repair or refuel a satellite like NASA's Restore-L. Autonomy is especially beneficial for deep space missions due to light time delay and limited resources for communicating with distant spacecraft. Now, one essential task for autonomous operations in space is navigation, which is the estimation of the state of a spacecraft. The spacecraft state can be represented as Cartesian position and velocity vectors, or equivalently as a set of orbital elements. A second estimation task that may be required is characterization, which can include estimation of the properties of the environment or of other agents. Properties of the environment can include characteristics of the orbited body, such as its gravity field, shape, and rotational motion, or atmospheric properties. And properties of other agents can include the orbits and physical properties of other spacecraft. When navigation and characterization are coupled, I've defined this class of estimation problem as SNAC, simultaneous navigation and characterization. SNAC is similar to a well-studied estimation problem called SLAM, simultaneous localization and mapping. However, SLAM is restricted to characterization of a single aspect of the environment, a physical map. So in this way, SLAM can be considered a subset of SNAC. Let me just give a few quick examples of SNAC. So one example is the GRACE mission, where the navigation of 2 spacecraft was coupled with the estimation of the Earth gravity field. Another example is the NASA Starling mission, where the navigation of 1 or more observer spacecraft is coupled with the estimation of the orbits of target spacecraft. Final example is asteroid rendezvous missions like Dawn, where the spacecraft navigation is usually tightly coupled with the estimation of the asteroid gravity field, and can also be coupled to some extent with the estimation of the asteroid rotational motion and 3D shape. Unfortunately, the navigation and characterization algorithms for deep space missions are almost exclusively executed offline and on the ground, which is also often the case for Earth orbiting missions. So what prevents navigation and characterization from being completed autonomously? First, the algorithms must be robust enough to operate dependably without human intervention. Whether in Earth orbit or deep space, the spacecraft is subject to numerous complex forces, and the resulting dynamics are nonlinear. The algorithms need to be robust to system nonlinearities as well as errors in the model of spacecraft dynamics, including contingencies like thruster malfunctions. The estimation algorithms must also be computationally efficient enough for onboard implementation. And computational resources on board spacecraft are typically very constrained, especially for small spacecraft. And this constraint is particularly relevant given the current trend of spacecraft miniaturization, illustrated in this figure here. As an example, this is a flight processor in our lab, which has an 800 megahertz processor. So the goal of my research is to enable more autonomous operations in Earth orbit and deep space through the development of novel algorithms for navigation and environment characterization that are more robust and computationally efficient than the state-of-the-art. So to accomplish this goal, my approach consists of 4 steps. First, the derivation of new algorithms to improve the robustness of navigation to dynamics errors and system nonlinearities. Then the development of new techniques for robust shape reconstruction of celestial bodies. Finally, a new algorithmic architecture for autonomous characterization of asteroids, including estimation of the asteroid gravity field, 3D shape, and rotational motion. Each new contribution must be computationally efficient enough for onboard execution and must be validated numerically and compared to the state-of-the-art. And I'll give just a quick overview of the relevant state-of-the-art and key limitations. So in general, navigation and characterization can be summarized as this task of estimating a state vector x given a set of measurements z and some nonlinear dynamics and measurement models. This task can be accomplished using either batch or sequential estimation techniques. In batch estimation, measurements recorded at different times or epochs are all processed at once to get an estimate of the state vector x hat and an associated error covariance p. This is the uncertainty of the estimate. In contrast, sequential estimation takes an initial estimate and covariance and updates these quantities each time a new set of measurements is recorded. The most common sequential estimation approach is Kalman filtering, and Kalman filtering is typically used for onboard navigation because it requires less memory and computational resources than batch techniques. So just to make sure we're all on the same page here, I'll give a quick overview of Kalman filtering. The Kalman filter can be separated into a time and a measurement update. So let's consider the case of navigation where the state vector to be estimated is the position and velocity of the spacecraft. So in the time update, we start with an initial estimate of the spacecraft state at time step k-1, taking into account all the measurements through that time step. We also have an associated error covariance p, which is the uncertainty in this estimate, and it's represented by this red uncertainty ellipse here. The model dynamics are used to propagate this initial state estimate forward in time to time step k, and the associated error covariance of that estimate here in purple is a sum of two terms. The first term in orange is the initial covariance propagated using the dynamics model, and the second term in green is the process noise covariance Q. And this term will become very important later in my presentation. So there are always going to be differences between the modeled and true spacecraft dynamics, and the additional uncertainty in this propagated state due to dynamics modeling errors is captured through this term Q, the process noise covariance. And this term is important because if it's not accurately modeled, it can result in very poor estimation. So that was the time update. Now in the measurement update, a set of measurements are used to correct the state estimate as well as the associated error covariance. And the output is the state estimate and error covariance at time step k, taking into account all the measurements through that step. And each time a new set of measurements is available, this time and measurement updates are repeated. So although the Kalman filter was originally derived for linear systems, there are many variants for nonlinear systems. The most common approach is the extended Kalman filter, or EKF, which linearizes the system through a first-order Taylor series expansion. However, in space applications, there's been a lot of interest recently in the unscented Kalman filter, or UKF, because it better captures system nonlinearities through the unscented transform. Particle filtering techniques, which use Monte Carlo methods, are typically too computationally expensive for execution on board a spacecraft. So this figure just gives a little example of the benefits of the unscented transform used in the UKF. So here, a Gaussian 2D vector is passed through a nonlinear transformation. The true mean and covariance, here in black, are well matched by the unscented transform in blue, but are poorly matched by the linearization in red. So although the UKF is generally more accurate than the EKF, it is also more computationally expensive, which can make it difficult to implement the UKF on board. So as I mentioned, the performance of navigation through Kalman filtering is heavily dependent on the realism of the modeled process noise covariance, Q. There are many approaches to modeling Q. One common approach is to manually tune a diagonal Q. This is a very ad hoc approach that does not consider the underlying system dynamics, and it doesn't scale Q for different propagation interval lengths. Another approach is to consider the effects of errors in modeling specific forces, for example, gravity. And although these models can be very accurate, they're also typically too computationally expensive for onboard implementation. State noise compensation, or SNC, is another approach which treats the process noise as unmodeled accelerations acting on the spacecraft that are a white noise process. Unfortunately, there's a lack of analytical SNC models, and analytical models or closed form models are desirable for their computational efficiency. Final one technique here I want to mention is dynamic model compensation, or DMC, where the unmodeled accelerations on the spacecraft are directly estimated by augmenting the state with empirical accelerations. However, this does increase the size of the estimated state vector, which increases the filter computation time. Alternatively, The process noise covariance can be estimated through adaptive filtering techniques. Unfortunately, most current adaptive filtering algorithms are not directly applicable to autonomous navigation, either due to computational cost or overly restricted assumptions like the assumption of a linear time invariant system. Current methods also don't constrain the estimate of Q according to the underlying dynamics and often use ad hoc methods to ensure that Q is posit semi-definite, which is a requirement for direct use in a common filter. So now switching gears a little bit, for deep space missions, a shape model of the orbited body is typically required for both mission operations and science objectives. The shape model can be constructed using LiDAR as one approach. However, methods using optical imagery are desirable because cameras have a relatively low size, weight, power, and cost. The most common optical approach is stereo photoclinometry, or SPC. And the great thing about SPC is that it is robust to changes in perspective and lighting conditions because it simultaneously creates topography and albedo maps. It can create very high resolution models. However, SPC is not well suited to autonomous operations because it requires significant human oversight, and it's much too computationally intensive for onboard execution. So another type of shape model is a spherical harmonic shape model, which is particularly beneficial because it can be easily used to infer characteristics of the body mass distribution. However, the traditional least squares approach to estimate a spherical harmonic shape model often overfits the data, resulting in large false surface protrusions in the modeled shape. There's currently a lot of interest in small bodies such as asteroids for their scientific value, as well as the potential to utilize their resources and prevent future collisions with the Earth. For small body missions, estimation of the body gravity field, 3D shape, and rotational motion is essential for safe and fuel-efficient operations near the body and to meet science objectives. So there have been a lot of very successful small body missions, but they have required significant human oversight and extensive use of highly subscribed ground-based resources, such as the NASA Deep Space Network, which is used for spacecraft communication and tracking. And although this approach is proven and reliable, it does have significant drawbacks. Mission operations are expensive, and the spacecraft is slow to react to its environment due to lifetime delay and gaps in communication with the Earth. So now I'll go over 5 key contributions that I've made to enable more autonomous spacecraft navigation and environment characterization. My first contribution is new analytical or closed form models of the process noise covariance. So if you recall, I mentioned earlier that state noise compensation is one of these common methods used for modeling the process noise covariance of a spacecraft state. It models the process noise as unmodeled spacecraft accelerations that are a zero mean Gaussian white noise process. Now, assuming a linearized system, this is the resulting expression for the process noise covariance, where phi is the state transition matrix, gamma is the process noise mapping matrix, and Q tilde is the power spectral density, which captures the strength of the unmodeled accelerations. So this integral can be evaluated numerically, but analytical solutions are desirable for their computational efficiency, which really is an important consideration for onboard execution. Currently, there's only one available analytical approximation of this integral, but it's restricted to a Cartesian state and a small propagation interval dt. Until now, there were no analytical solutions of this integral for orbital element states or relative spacecraft states. So first, I was able to use the assumption of a circular orbit to derive new analytical model for a Cartesian state, which is valid for much longer propagation intervals for near circular orbits than this state-of-the-art method. Then I used each of these assumptions, a small propagation interval and near circular orbit, to derive new analytical models for orbital element states. So here, each blue box represents a new analytical model. And for the sake of time, I'm not going to go into the mathematical details of these models, but it's important to know that all these models assume two-body motion and further assume either small propagation interval or circular orbit. But I was able to extend these models to long propagation intervals for perturbed eccentric orbits by dividing the propagation interval tk minus 1 to tk, dividing it into n smaller subintervals, which are defined using these t-bar. Then this single integral for Q can be equivalently written as this sum. So what's going on here is for each term in this sum, Q is computed over one of these smaller subintervals and then is propagated to the end of the interval. Then each term of the sum is added to get the total process noise covariance. So the benefit of writing Q like this is that you can use an analytical approximation of Q that holds for small propagation intervals for just each subinterval, and then you can use a high fidelity state transition matrix here to take into account any effects that were neglected in the computation of Q. So a key insight here was that state transition matrices for relative spacecraft motion can be used here by considering the estimation error as a relative spacecraft state, where the chief spacecraft is the estimated state and the deputy spacecraft is the true state. So then you can use any of the many analytical state transition matrices for spacecraft relative motion here that fully account for eccentricity and account for different perturbations. And here the accuracy of Q increases as the number of subintervals increases, so the number of subintervals should be chosen to balance accuracy and computational cost. So that was all for absolute spacecraft states. I was able to extend those analytical models to relative spacecraft states, which describe the motion of one spacecraft relative to another. So a relative spacecraft state, delta x, is just a nonlinear function of the absolute states of the chief and deputy, which can be parameterized using Cartesian coordinates or orbital elements. For small intersatellite separation, the relative state dynamics can be linearized about 0 intersatellite separation. And then for large intersatellite separation, it can be assumed that the unmodeled accelerations of the chief are uncorrelated with those of the deputy. So using either of these two assumptions, the process noise covariance of the relative spacecraft states can be written as an analytical function of the process noise covariances of the chief and deputy states. So I validated these new analytical process noise models by comparing them to numerical solutions of this integral attained through fourth order Runge-Kutta numerical integration. The reference truth orbits consider non-spherical Earth gravity, atmospheric drag, third body effects, and solar radiation pressure. This approach that I presented for modeling the process noise covariance of orbital elements can be applied to any orbital element state, but I'm going to use the equinoctial orbital elements here as an example. So this plot shows a comparison of the analytical process noise models that assume a small propagation interval, delta t. And the plotted error metric is delta t min, which is just how long the propagation interval can be before there's a 10% error in the model. The x-axis here is the orbit eccentricity. So you can see that my new model for equinoctial elements in purple can be applied for much longer propagation intervals than the commonly used model for Cartesian states in green. So now let's consider a second error metric, delta max, which is the maximum fractional error in the model for propagation interval lengths of up to one orbit. So this error metric is plotted, here's a function again of the orbit eccentricity. The solid lines are Cartesian models, and the dashed lines are equinoctial element models. So first let's look at the green and purple lines, which are the models that assume a small propagation interval. So as expected, these models don't perform well here because the propagation interval can be long all the way up to a full orbit. The red lines are the models that assume a circular orbit, and you can see that there's very low errors for when the eccentricity is low, but then obviously the errors increase as eccentricity increases. But important thing to note is that the equinoctial model can be used for higher eccentricities than the Cartesian model. So then the blue and black lines are models that divide the propagation interval into either 4 or 8 subintervals. For each subinterval, the analytical models that assume a small propagation interval are used. And so increasing, as you can see here, increasing the number of subintervals going from blue to black improves the accuracy. And you see again that the equinoctial models are more accurate than the Cartesian models. So now let's fix the eccentricity and add a second spacecraft. As illustrated in this figure, the two spacecraft are in near circular orbits and are separated primarily in the long track direction as described by delta lambda naught, which is the initial relative mean longitude. The correlation of the unmodeled accelerations of the two spacecraft is modeled as decaying exponentially as the interspacecraft separation increases. So we're just saying that as the spacecraft get further apart, their unmodeled accelerations are less correlated with one another. So this plot here compares the performance of the small and large separation frameworks for relative spacecraft states when leveraging the new absolute models that assume a circular orbit. So the x-axis of this plot is roughly the interspacecraft separation, and the y-axis is, again, the maximum fractional error for propagation interval lengths of up to a full orbit. So in these plots, the Cartesian models are blue and the equinoctial models are red. The error, you can see that the error of the large separation models, which are the solid lines, their error increases for small separations due to the assumption that the chief unmodeled accelerations are uncorrelated with those of the deputy. On the other hand, the small separation framework fully accounts for the correlation between the chief and deputy unmodeled accelerations. However, the error of the small separation models, which are the dashed lines, increases as interspacecraft separation increases due to the linearization about zero interspacecraft separation. So the real key takeaway here, though, is that for any intersatellite separation, you can get a small error by using either the small or large separation framework. So that was my first contribution, new analytical models of the process noise covariance. I leveraged these models in my next contribution, which is new techniques for adaptively estimating the process noise covariance. So for state noise compensation and dynamic model compensation, Q is given by this integral that we saw earlier. The difference here is that DMC augments the state with empirical accelerations to estimate the error in the modeled spacecraft accelerations. The key limitation, though, of any process noise model, including SNC and DMC, is that they require some a priori knowledge to tune the model parameters, which may not be available. Additionally, any tuning of a process noise model is invalidated when the process noise statistics change, which can happen, for example, due to a transition to a different orbit or a mission contingency like a malfunctioning thruster. So in this case, the tunable parameter is Q tilde. Alternatively, Q can be estimated through adaptive filtering techniques, but recall that many existing adaptive filtering approaches aren't directly applicable to onboard navigation because they're either too restrictive or computationally intensive. Covariance matching is one adaptive filtering technique that has been investigated for navigation because it is computationally efficient and simple. So the covariance matching estimate of Q here, it's given as an average over a sliding window of length n of filter output, where P is the filter error covariance, V is the state transition matrix, and delta X is the correction of the state estimate and the measurement update. So a requirement here is that key has to be positive definite, positive semi-definite to be used directly in a common filter. But this estimate here has no guarantee on the definiteness of Q. So the most common approach that people take is to assume that these first two terms are negligible. And this guarantees a positive semi-definite Q, but the estimate is biased. This estimate also doesn't consider the underlying system dynamics. It can't extrapolate Q over a long propagation interval, for example, due to a measurement outage. And it also can't consider process noise that is correlated in time. So my unique approach here was to take process noise covariance modeling and estimation and fuse them to overcome their limitations. Specifically, I fused SNC with covariance matching through a weighted least squares optimization to yield a new adaptive filtering technique called adaptive SNC, or ASNC. Similarly, I fused DMC with covariance matching to yield adaptive DMC, or ADMC. So I'll give just a really high-level overview of these new algorithms. The SNC and DMC models of Q are symmetric and also linear in Q tilde, the model parameter. I'll assume here that Q tilde is a diagonal matrix. So a vector of the unique elements of Q can be written as a matrix X times a vector that is the main diagonal of Q tilde. And for SNC, this X is easily taken from my new analytical process noise models I just talked about. So after each filter call, ASNC and ADMC find the diagonal q tilde that best matches the modeled q to the corresponding covariance matching estimate, where the first two terms of the covariance matching estimate are not neglected. Then the estimated q tilde is used to compute q at the next filter call. Here the weighting matrix W is the theoretical covariance of the covariance matching estimate. And note that the q tilde is constrained element-wise to be between lower and upper bounds, which can be chosen based on any available a priori knowledge. But if no a priori knowledge is available, the upper bound can just be neglected. But the lower bound must always be at least 0 to ensure that the resulting q is positive semi-definite. So this optimization for ASNC and ADMC is an inequality-constrained quadratic program, which is convex. So it can be efficiently solved using readily available solvers. However, in a special case, the optimization can be solved extremely efficiently for a Cartesian spacecraft state and if the propagation interval is small. And I won't go into the mathematical details here for time, but in this case, the optimization can be solved analytically or in closed form. So now we'll show some numerical results for the new navigation, or for these new algorithms in 2 case studies. The first case study is a linear system. Let's consider a particle moving in one dimension along the x-axis. The Kalman filter estimates the position and velocity of the particle using range and range rate measurements, which are just direct measurements of the estimated state. And throughout the simulation, the particle is subject to this unknown perturbing sinusoidal acceleration. So these plots show the mean absolute error in position, velocity, and acceleration, averaged over 1,000 Monte Carlo simulations for, you can see here, several different process noise techniques. The x-axis is the initial guess of the process noise power spectral density. The black line is when no process noise is modeled in the filter, which, as you can expect, results in large errors. The yellow and red lines are when using SNC and DMC, which only do well for a good choice of q tilde. In contrast, the new ASNC and ADMC algorithms, which are the pink and green lines, perform well regardless of this initial guess of q tilde. The new algorithms also perform significantly better than covariance matching in blue and 2 other state-of-the-art adaptive techniques shown in teal and gray. ADMC in pink performs a little bit better than ASNC in green because the measurement rate and accuracy were sufficient to accurately track the unmodeled acceleration. So, for example, these plots show acceleration tracking for DMC and the newly proposed ADMC when the algorithms are given a very large initial guess of q tilde. The red line is the true unmodeled acceleration, and the black line is the estimated empirical acceleration. So as you can see, DMC greatly overestimates the unmodeled acceleration, while ADMC is able to converge down to a correct value of q tilde and track the unmodeled acceleration well. So the second case study is a more realistic and challenging scenario. It's of 2 spacecraft orbiting the asteroid Eros. The spacecraft orbits have a semi-major axis of 40 kilometers, and the simulation lasts for 4 orbits. The reference truth orbits are propagated considering a degree in order 15 gravity field of Eros, some third body effects, and solar radiation pressure. The reference truth also includes an out-of-plane maneuver that changes that spacecraft right ascension of the ascending node by 11 degrees. So here a UKF estimates the Cartesian states of the 2 spacecraft using inner spacecraft range and range rate measurements, as well as camera pixel measurements of tracked landmarks on the asteroid surface. The measurements are simulated every 5 minutes and corrupted with Gaussian noise according to this table. So the important thing here is that the process noise was very large because the filter dynamics model only considers 2-body gravity and J2 of the asteroid. So this table shows the mean 3D errors in position and velocity averaged over 1,000 Monte Carlo simulations for 4 different adaptive process noise techniques. In this, we have 2 scenarios here. In the perfect maneuver scenario, the maneuver is modeled in the filter perfectly, And in the imperfect maneuver scenario, the maneuver modeled in the filter was corrupted by random errors, where the uncertainty in maneuver magnitude was 15% and uncertainty in the maneuver direction was half a degree. So clearly, covariance matching performed the worst. IMM here is another state-of-the-art adaptive process noise technique. And although it did do fairly well, it is by far the most computationally expensive because it requires two filters to be run in parallel. IMM also requires upper and lower bounds on the process noise covariance, and the choice of these bounds really heavily impacts the performance. So ASNC performed better than covariance matching in IMM, and ADMC was able to further improve performance. I also just want to quickly mention that ASNC was tested with hardware in the loop by another PhD student in my lab, Jeff Park. He applied ASNC to a scenario where one spacecraft estimates the relative position and orientation of another spacecraft at close range using only monocular images. Each image is processed by a convolutional neural network, or CNN, and the output of that CNN is fed to a UKF as measurements, and then the UKF estimates the relative spacecraft pose. So the images used in his simulations were captured in our lab's robotic testbed shown here, which has light boxes to simulate the illumination conditions of space. One robotic arm holds a spacecraft model, and the other arm holds a camera that records realistic images. So the plots on the right show position and orientation errors for the CNN output in gray, a UKF with a fixed Q in blue, and a UKF with ASNC in red that also leveraged one of my new analytical process noise models. And as you can see, ASNC in this case resulted in the lowest errors. All right, so the third contribution is quick. It's a new technique to reduce the computation time of a UKF with no loss of accuracy. So as I mentioned earlier, the UKF, or unscented common filter, has received increased interest in space applications because it's generally more accurate for nonlinear systems than the commonly used EKF. But implementing a UKF on board can be challenging because it is more computationally expensive than the UKF in general. So in the UKF, sigma points are generated according to this rule. The 0 sigma point, it's just the mean state estimate, and the other sigma points are the mean state estimate plus or minus a column of this matrix A. And A has a special property that it's a lower triangular matrix. The sigma points are passed through the nonlinear dynamics and measurement models. And in space applications, the spacecraft dynamics models are often very computationally expensive, especially if non-spherical gravity is considered. So passing these sigma points through the dynamics models can heavily dominate the total filter runtime. So I realized that because of these zeros in the top right of A, dynamics and measurement model computations from the 0th sigma point can be reused. Well, that these dynamics and measurement model computations, they're repeated at other sigma points. So my new approach is to reuse these dynamics and measurement model computations from the 0 sigma point for the other sigma points, and to also choose the state ordering, the ordering of the state vector to maximize the computational savings. This technique reduces the UKF runtime with no loss of accuracy, which facilitates onboard implementation of the UKF. So this new technique is actually used in the digital and Artemis navigation payloads that our lab is developing, which will both be deployed on upcoming flight missions. In the particular case of Artemis, my new technique reduces the UKF runtime by about 50%. So now getting to my fourth contribution, which is an improved technique for shape reconstruction of celestial bodies. So if you remember, I mentioned earlier that SBC is the most common optical shape modeling technique, but it requires too much human oversight and computation time for onboard execution. Another approach to shape modeling is spherical harmonics, as shown in this equation, which provides the surface radius r at any longitude lambda and latitude phi. Here, A bar and B bar are coefficients that describe the shape of the body, where n is the degree of the coefficient and m is the order. So in practice, this model is truncated to some maximum degree, capital N. A larger degree model results in more of these A bar and B bar coefficients and can provide higher shape resolution. Now, if we have a set of points on the body's surface, we can use them to estimate the A bar and B bar coefficients through a least squares fit. So here S is a vector containing all of the shape coefficients to be estimated. R is a vector containing all the radii of these surface points, and A is the model matrix. So when you solve this optimization, you can get a good spherical harmonic model like this. However, if the degree of the model is too high and the points are sparse, the model can overfit the data, which gives poor results like this. Now, any of us would know immediately that this is a bad shape reconstruction, right? Because we know that small bodies like asteroids typically look something like this. So my contribution here was to incorporate this a priori natural intuition of what celestial bodies typically look like, to include that into the estimation of the shape model, which I do through the addition of this regularization term here. The key is that this, it's called the Tikhonov matrix gamma. It's based on empirical data of the shape characteristics of small celestial bodies. What it's really doing is penalizing large values of high degree coefficients in order to get a surface that is more similar to what we would expect a priori. Nu here, this parameter nu, is a weighting parameter that determines the importance of surface smoothness relative to fitting the data. There are a lot of different techniques for selecting and quote unquote optimal nu, but I use the method of generalized cross-validation. Now, in order to quantify the uncertainty of the shape model, it's important to take into account that the shape model we've estimated, it only includes a finite subset of the infinite number of shape coefficients that would be required to describe an arbitrary shape. And we can approximate the uncertainty of the shape coefficients that are omitted from our estimated shape model by using this equation here, which is actually what the regularization matrix gamma is based on. So this is a model that approximates the root mean square of all the coefficients of degree n as a constant k over the degree of the shape coefficients to a power alpha, where alpha is a constant. So as illustrated in this figure, k is estimated by fitting this theoretical model in orange to the empirical values of the estimated coefficients shown in blue. The estimate of the constant k can then be used to approximate the variance of the ith omitted shape coefficient here. Then the uncertainty of the shape coefficients that we estimated, S, can be computed as a function of the covariance of the omitted shape coefficients, P of O, the covariance of the surface points used to estimate the shape model, P of L, and the regularization parameters. And then use that to quantify the uncertainty of the shape model radius at any point on the surface, which is a function of the uncertainty of our estimated coefficients plus a function of the uncertainty of the omitted coefficients that we're not taking into account in our model. Now, once a shape model has been estimated, it's not computationally efficient to reconstruct your shape model from scratch whenever new data is available or whenever the degree of the shape model needs to be increased. So we can instead incorporate new shape coefficients into the set of estimated coefficients by approximating the distribution of each new coefficient as Gaussian with a mean of 0 and the approximate variance I just discussed on the previous slide. And then when new surface point estimates are available, they can be used to sequentially update the current set of estimated shape coefficients and their uncertainty through what is just essentially the common filter measurement update equations, but being careful to include the uncertainty of the omitted shape coefficients, uncertainty of these new surface point estimates, and what was previously the uncertainty of the shape coefficients. So now for some numerical results. I randomly sampled 750 points on the surface of this triangular mesh model of the asteroid Eros and used those points to estimate spherical harmonic models of different degree using 3 approaches. So first is without any regularization in black, just strictly squares. Regularization using a common Tikhonov matrix in green. And then my new approach in blue. The y-axis is the root mean square error of the model, the estimated model. So you can see that although all 3 approaches provide similar results for low degree models, the proposed approach in blue, provides substantially better accuracy for higher degree models by preventing overfitting. And it's very remarkable here that the error of the new approach for a degree 35 model is actually 2.5 times smaller than the lowest possible error when using either of the other two approaches. So for further illustration, here are the degree 16 shape models produced by each of the three approaches. Clearly, the new approach provides a much better shape reconstruction. And I did this same test, but where the sampled surface points were first corrupted with random noise, Gaussian noise with a standard deviation of 100 meters. And you can see here that it resulted in similar trends. So these plots show the radial uncertainty of the model at each latitude and longitude. And this is for specifically the degree 35 model that was estimated using my new approach. So the total radial uncertainty here is the root mean square of the uncertainty due to errors in the estimated coefficients and then uncertainty of the omitted coefficients that we didn't include in our shape model. The red dots here are the sampled points used to construct this shape model, and as expected, there are regions of large uncertainty in yellow where no data was available in the construction of the shape model. So this plot can be used to inform planning for future observations in order to reduce these high uncertainty regions. The radial uncertainty due to omitted shape coefficients is about 50 meters in this case, which is a theoretical lower bound on this total uncertainty of the shape model. So if a shape model is desired that's more accurate than 50 meters, then this plot indicates to us that we would need to construct a higher degree shape model. This is a quick numerical example of sequentially updating the shape model. The plot on the left is a degree 10 model that was generated using 250 surface points. This model is then expanded to degree 20 and sequentially updated with 1,000 additional points. This sequential update, you can see it cut the error in about half. Now, in contrast, this plot on the right is a degree 20 model that was generated using all those 1,250 points at once, which resulted in a slightly lower error than the sequentially updated model in the middle, but there's a trade-off since sequentially updating the model is much more computationally efficient. All right, I think I'll grab a quick drink here. All right, so now I'll go over my last contribution, we're almost there, which is the preliminary design of a new mission concept called ANS, which stands for Autonomous Nanosatellite Swarming. ANS consists of a mothership and multiple smaller nanosatellites that all cooperate to autonomously characterize an asteroid. This is in contrast to completed asteroid missions, which have depended extensively on human oversight and also ground-based resources. So the ANS concept of operations can be roughly divided into these three phases. In the first phase, the mothership approaches the asteroid, enters a high altitude orbit where a coarse initial characterization of the body gravity field and rotational motion is completed with ground in the loop, similar to completed missions. But the idea is that this first ground in the loop phase is relatively brief, and I'll assume here that it has already been completed. So the remaining phases are autonomous. So in the second phase, the mothership releases the nanosatellites, and as these spacecraft all co-orbit the asteroid, they record intersatellite radio frequency, RF, pseudo-range, and Doppler measurements while recording images of the asteroid. So these intersatellite measurements and asteroid images are used together in a novel framework to simultaneously navigate and characterize the asteroid, in other words, SNAC. In the third phase, the swarm geometry is reconfigured over time to improve estimation. So now for an overview of this ANS framework, the spacecraft record these intersatellite one-way pseudo-range and Doppler measurements, as well as images of the asteroid. These images are processed to optically track landmarks in the images over time using SIFT features. And this block provides two important outputs. The first output is pixel measurements of tracked landmarks. These are 2D locations of tracked landmarks in the images. The second output is initial 3D position estimates of new landmarks to start tracking. So these new landmark position estimates are obtained through stereo vision, where the same feature is detected in images taken by more than one spacecraft at the same time. This optical landmark tracking block is the work of another student in my lab, Caitlin Dennison, so I won't go into any more details on this block. The landmark pixel measurements and the inter-satellite pseudorange and Doppler measurements are used in the UKF to estimate the spacecraft states and asteroid properties. Here in the UKF, the pseudorange between each pair of spacecraft is modeled as the geometric range between the spacecraft plus biases that are due to the offsets of the nanosatellite onboard clocks with respect to the mothership clock. The Doppler measurements are just the time derivative of the pseudorange measurements. Pixel measurements U and V of tracked landmarks are modeled through this simple pinhole camera model. The UKF specifically estimates the parameters listed in this table, which are the Cartesian state and solar radiation pressure coefficient of each spacecraft, the clock offset and drift of each nanosatellite with respect to the mothership, the gravitational parameter of the asteroid and its spherical harmonic gravity coefficients up to a specified degree, parameters describing the asteroid rotational motion, and lastly, the 3D body fixed positions of landmarks that are currently being tracked. And the UKF estimates these parameters are fed back to improve optical landmark tracking. I should also mention that a coarse initial estimate of all these parameters is provided by that initial ground in the loop initialization, except for landmark positions. Initially, no landmarks are tracked, and the UKF has no landmark positions in its state vector. New landmarks are autonomously incorporated into the filter state throughout the mission through stereo vision from the optical landmark tracking block. Also throughout the mission, different features enter and leave the spacecraft fields of view. And since SIF feature matching isn't robust to very large changes in perspective and illumination conditions, features that have not been seen for a specified amount of time are then no longer tracked and are removed from the filter state. However, estimates of landmarks removed from the filter state are still retained in a landmark database. Also want to mention that this UKF uses my new technique to reduce the computation time with no loss of accuracy, and it also uses my new ASNC algorithm to adaptively estimate the process noise covariance of the spacecraft states. The process noise covariances of the relative clock states are also modeled carefully according to the accuracy of the onboard clocks. Then at any point during the mission, the landmarks that are stored, landmark estimates stored in the landmark database can be used to generate a spherical harmonic shape model using the new regularization method I developed. Now, in the full ANS concept, the UKF estimates would be used in guidance algorithms to determine the desired orbit geometry, which would be achieved by control algorithms commanding the spacecraft actuators. However, in the numerical results I'll present next, I'll just focus on what's in this red box. So we simulated ANS in MATLAB for a 3 spacecraft swarm orbiting the asteroid Eros for 10 orbits. The spacecraft have a semi-major axis of 45 kilometers and are separated primarily in the along track direction, as you can see in this illustration. The truth dynamics include the asteroid gravity up to a degree in order 15, sun third body effects, and solar radiation pressure. The clock errors are simulated stochastically, resulting in small errors in the measurement time tags of each spacecraft. The asteroid images are generated using OpenGL, and you can see a sequence of these images here for one spacecraft. And as mentioned earlier, the filter estimates the state, which includes spacecraft states, relative clock offsets, and asteroid properties. Measurements are nominally simulated every 5 minutes with these modeled uncertainties in this table. So as far as the results, first I'll show how the UKF performed. These plots show the estimation error in black and the 3 sigma formal uncertainty from the filter in gray. So for a filter that's performing well, you would expect these estimation errors to be mostly within this gray region, the 3 sigma uncertainty. So here the parameters are the asteroid gravitational parameter, the C20 gravity coefficient, asteroid spin rate, the x components of the mothership position and velocity, and the clock offset of the first deputy. So you can see that for all these parameters, the uncertainty decreases significantly and the filter remains consistent, meaning that the errors are within the theoretical error bounds. My new technique was able to reduce the filter runtime by 11 to 83% as compared to a traditional UKF, depending on the number of landmarks currently tracked. This table shows the a priori uncertainty in each estimated parameter before the simulation began. And it also shows the root mean square error and 1 sigma theoretical uncertainty over the last orbit of simulation. So you can see that the root mean square errors are fairly similar to the theoretical 1 sigma uncertainties, which indicates a well-functioning filter. Notice in particular that the gravitational parameter uncertainty decreased by nearly 2 orders of magnitude. The plot on the right shows the root mean square for each degree of gravity coefficient. The black line is the true coefficient magnitudes. And the blue line is the a priori 1 sigma uncertainty. And you can see that the final errors in purple are near the final 1 sigma uncertainties in orange, which again indicates a well-functioning filter. The gravity coefficients here were estimated to an uncertainty less than their magnitude up through about degree in order 6. For comparison, the NEAR mission was able to estimate the gravity coefficients of Eros through degree in order 10 to an uncertainty less than the coefficient magnitudes. However, NEAR had a full year of data, including data at much lower altitudes where the gravity field is more observable. So it seems likely that the accuracy of ANS could be competitive with a traditional ground-in-the-loop mission. The spacecraft position uncertainty here is also similar to what the NEAR mission achieved at this altitude. The left plot is the asteroid shape model used to generate images, our truth shape model. The middle plot is the final landmark database in blue superimposed on the true shape. And this final landmark database was used to generate a degree 10 spherical harmonic shape model here. And even though you can see there were no landmarks in the database on top of the asteroid because this was in shadow throughout the simulation, despite that, the shape reconstruction was still pretty good. In fact, the root mean square error of this estimated shape was only 3.9% of the average asteroid radius. Here are some average and worst case runtimes of the ANS algorithms for a MATLAB implementation on just a desktop PC. We haven't put in much effort yet to optimize these computation times, so they really represent upper bounds on the computation time that can be likely improved significantly. Main takeaway here is that the total runtime for each measurement interval, which lasts 5 minutes, the total runtime was about 1.5 seconds for the mothership and about 0.6 seconds for each nanosatellite. The shape reconstruction algorithm took about 10.8 seconds, but that was only executed once during the simulation just to get an initial shape model, which can then be quickly updated sequentially with future data. So now to finish up here, I'll quickly review my contributions and discuss some future work. So if you recall, my first contribution was new analytical or closed form process noise covariance models for absolute and relative spacecraft states, parameterized using both Cartesian coordinates and orbital elements. These models can be accurately applied to closed orbits of arbitrary eccentricity, and every model is guaranteed positive semi-definite, which is required for integration in a Kalman filter. And since these models are analytical, they're very computationally efficient, so they can be easily implemented on board to improve the robustness of autonomous navigation to dynamics modeling errors. The second contribution is new techniques to adaptively estimate the process noise covariance. The new techniques are very well suited to onboard navigation because they're computationally efficient and they don't rely on restrictive assumptions. These techniques guarantee the process noise covariance is positive semi-definite. They consider the underlying spacecraft dynamics and can incorporate any available a priori knowledge of the process noise. These techniques are important because they increase navigation robustness to dynamics modeling errors in very challenging situations where the process noise statistics may change over time, for example, due to a thruster malfunction, or when the process noise statistics are poorly known a priori, which is typically the case for small body missions. The third contribution was a technique to reduce the computation time of UKF with no loss of accuracy. This facilitates onboard implementation of the UKF, which is more accurate than the commonly used EKF. The fourth contribution was a new regularization procedure for more accurate and robust shape reconstruction using spherical harmonics. This new regularization that I came up with prevents overfitting, and it's much more computationally efficient than the commonly used SPC technique. I also derived methods to quantify the uncertainty of the shape model and to sequentially update the shape model. All right, the last contribution was a new preliminary multi-spacecraft mission concept for autonomous asteroid characterization called ANS. I developed a novel algorithmic framework that leverages the first four contributions in order to simultaneously provide navigation, time synchronization, and asteroid characterization, including estimation of the asteroid gravity field, 3D shape, and rotational motion. And each of these 5 contributions was validated numerically and compared to the state of the art. I also want to note that the first 2 of my contributions for modeling and estimating the process noise covariance have also been validated with hardware in the loop by another student in my lab using our lab's robotic testbed. Also, the computationally efficient UKF has been incorporated into navigation payloads in our lab that will be implemented on board upcoming flight missions. And really, the potential impact of this work is to enable more autonomous operations in Earth orbit and deep space. This added autonomy can reduce mission costs and can also alleviate the burden on ground-based resources. So as far as future work, the same approach that I developed to derive analytical SNC process noise models could be used to obtain analytical DMC models. New adaptive filtering techniques could be derived by fusing SNC and DMC with other adaptive filtering techniques other than just covariance matching. The shape reconstruction methodology could be applied to ellipsoidal harmonics and could potentially be extended to shape reconstruction of spacecraft in orbit. The ANS mission concept could be applied to additional small bodies such as complex rotators and binary asteroids. It would also be very helpful to eliminate the need for that initial brief ground-in-the-loop initialization. Future work should also include integrating that ANS estimation pipeline with guidance and control algorithms and testing that fully integrated system with hardware in the loop. Our lab has a lot of tools that could potentially be used for future hardware in the loop testing advance. This includes FlatSats with representative spacecraft microprocessors, an optical stimulator where a spacecraft camera captures images from a small screen where the space images are rendered, and also a robotic testbed that can provide realistic space imagery. I also want to mention that my research resulted in 6 first author publications, including 4 conference papers and 2 peer-reviewed journal articles. I'm also a co-author on 2 additional submitted journal articles. And I guess that's it before I go into acknowledgments. So I'll go ahead and stop there. Thank you everyone for your attention.